Welcome to the lecture series on process integration. This is module 5, lecture 5. The topic of this lecture is design of single pinch problem. I have told you that there are three types of problems are generally encountered. The first one is threshold problems, in which either hot utility is required or cold utility is required, but not both. Then second type of problem is the Henn problems with single pinch, and third type of problem is Henn problems with multiple pinch. The multiple pinch problems generally occur when we use multiple hot or multiple cold utilities. So, we have divided the design problem into three categories. The threshold problems, already we have discussed how the design can be made. In this lecture, we will see how the design of a single pinch problem should be done. In the single pinch problem also, we have divided this lecture into two type of problems. The first, in which the stream splitting is not required, and the second, where the stream splitting will be required. Let us first see the philosophy. The pinch represents the most constrained region of a design. This is the most important fact of a pinch design procedure. After all, delta T minimum exists between all and hot and cold streams at this pinch. As the delta T minimum is small, the heat exchangers which operate near the pinch or at the pinch operate at minimum delta T temperature difference, and hence the area of these heat exchangers are mostly large or high. Due to this, sometimes the concentration of area of the heat exchanger network at pinch is high, and these heat exchangers also contribute towards the total cost of heat exchanger network, and hence placing matches at and around pinch is very important. As a result, the number of feasible matches in this region is severely restricted. Quite often, there is a crucial or essential match. If this match is not made, this will result in heat transfer across the pinch and thus increase hot and cold utility usage. This we have also explained that if there is a passing of heat through the pinch or transfer of heat through the pinch, the taxation will be double. The cold and hot utilities will increase, plus the area required to pass on the additional amount of hot and additional amount of cold utility will be required also. So, the taxation is double. So, placing matches around pinch is very essential. In many times we also see in some other lectures that if I am not putting up proper matches at the pinch, the design will not conform to the area target results, and through area targeting generally we reach to the minimum area requirement, and the design will not conform to that minimum area requirement, maybe that it will show more area than the targeted area. And that is why in the pinch design methodology, we always recognize the pinch division, because it divides a bigger problem into two smaller problems at the pinch, because there is no heat flow through the pinch. That is why the upper pinch area or the lower pinch area, or we call it hot end or the cold end, are separate as far as heat exchange is concerned. The other rule is that start the design at the pinch, developing it separately into two remaining problems. So, design will be started at the point where the problem is most restricted, and then the method is to go away from the pinch, because when we go away from the pinch, the delta T increases. Now, the approach of pinch design is totally different than normal intuitive approach. The normal intuitive approach starts the design at the hot end or hot side, developing towards the cool side. When a design is started at the hot side, initial design decisions may later necessitate follow up decisions which violate the pinch. So, if we come from the hot side, hot end to the pinch, this may be possible that we will violate the pinch. That means, either we will not be able to maintain those delta T minimum temperatures, and if we do not maintain delta T minimum temperatures, we cannot guarantee the hot utility and cold utility requirements. Further, this may be possible that some heat will pass through the pinch when we design from the hot side and move towards the pinch, and we know that the penalty in such a case is double. On the other hand, when a design is started at the pinch, initial design decisions are made in the most constrained part of the problem and are less likely to lead to difficulties later. And based on this philosophy, the pinch design method starts from the pinch where the problem is most constricted and then moves away from the pinch. Thus, commencing a design at the pinch has the distinct advantage of allowing the designer to identify essential matches or topology options in the most constrained region of the design, which are in keeping with minimum utility usage and maximum energy recovery. The maximum energy recovery design will only take place when no heat passes through the pinch. If the heat passes through the pinch, we cannot call it maximum energy recovery design. And in a maximum energy recovery design, the requirement of utilities, which consist of hot utilities and cold utilities, are minimum. The pinch design method incorporates 5 important stages. The stages are: the Henn problem is divided at the pinch into 2 separate problems. This we know because no heat passes through the pinch, and that is why the upper part of the pinch and lower part of the pinch can be made separate, or they can be designed separately, because no heat flows between these two halves. The design of these separate problems is started at the pinch and developed moving away from the pinch. This we have explained in detail. At the pinch, essential matches, match options and stream splitting requirements are identified by applying the feasibility criteria. Then pinch gives some feasibility criteria based on which the matches can be put. They are different for hot end and they are different for cold end. Then whether to go for a splitting of a hot stream or a cold stream are also covered by some rules and regulation. When option exists at the pinch, the engineer is free to base his selection to suit the process requirement. The pinch design method allows the designer and offers the designer a lot of flexibility, and according to the process requirements, the designer can place a pinch heat exchanger. That means, the stream matching can be done based on the process requirement by the engineer. The heat load of exchangers at the pinch are determined using stream Teacup heuristic. This stream Teacup heuristic has a base on, it is based on the number of units target, and if we follow Teacup heuristic, which has been explained earlier, then number of units will be less, and if we do not obey this Teacup heuristic, the number of units may be more or it will be more in most of the cases. In case of difficulty, that is when we see increased in utility usage, a different heat exchanger topology at the pinch can be chosen, or the load on the offending matches can be reduced. Now, based on Teacup heuristic, many problems can arise, and to solve those problems, we can select different matchings, or we can reduce the load of a particular heat exchanger which the Teacup offers. Now, away from the pinch, there is generally a free choice. Why it is so? Because at the pinch the delta T minimum is minimum, or delta T is minimum at pinch, but when we go away from the pinch towards the hot end or towards the cold end, then the delta T available between the hot streams and cold streams increases. That means, we can say that it is diverged out from the pinch, the diversion takes place, both the streams diverge out, and hence the delta T increases. Once the delta T increases, then it is easier to put matches, because it will not violate the delta T minimum criteria. There we will see that away from the pinch, the binding of rules and regulations, which are CP rules and stream rules, at least CP rules can be violated to some extent till delta T minimum violation does not take place. So, from away from the pinch, we can somewhat dilute this CP rule. This we have seen many a times, but if we dilute the CP rules for pinch exchanges, then we will certainly violate the delta T minimum criteria. But if it is not a pinch exchanger and it is away from the pinch, then violating the rule to some extent, that is CP rule to some extent, will not violate the delta T minimum criteria. But in no case we can violate the delta T minimum criteria in the design. Why? Because if I violate the delta T minimum criteria in the design, then my hot utility requirement and cold utility requirement will change. When we design a heat exchanger network, it is for a fixed amount of cold utility and hot utility in a MER design specially. But when we go for a non-MER design, the hot utility and cold utility may increase or decrease. Now, it will not decrease, it will increase. Now, to demonstrate this design principles, we have taken a stream data. Here there are 2 cold streams and 2 hot streams. Supply, target temperature, delta H values, heat capacity flow rate ratio are given. The negative sign with the hot stream shows that the stream can give heat, and the positive sign for the delta H column shows that the streams will take heat. So, with the cold we have positive signs of delta H, and with hot we have negative sign of delta H. The MCP values, which is capital CPs, are also given for this stream table data. Now, once we use the stream table data and do the PTA analysis, problem table analysis, then we find that the hot utility requirement is 7.5 megawatt and the cold utility requirement is 10 megawatt. The delta T minimum for this problem is 10 degree centigrade, and the hot pinch is at 150 degree centigrade and cold pinch is at 140 degree centigrade, and the difference between the hot and cold pinch temperatures is 10 degree is equal to delta T minimum. Now, let us convert this stream table data into streams, grid diagram. So, the first stream has come from 2, this is 250 to 40 degree centigrade and hot pinch is 150, Cp value is 0.15. This fourth stream, which is a hot stream, starts from 200 degree centigrade, goes up to 80 degree centigrade, hot pinch temperature is 150, Cp values, capital Cp value is 0.25. Then cold stream 1, it goes from 20 degree to 180 degree. The cold pinch temperature is 140 degree. Cp value is 0.2, and third stream, which starts from pinch temperature, goes up to 230 degree centigrade and Cp value is 0.3. So, here we see that in the hot end there are 4 process streams plus 1 hot utility will be required, whereas for the cold end there are 2 hot streams and 1 cold streams and 1 cooling utility. So, this is the stream or grid diagram, and we have to design a heat exchanger network for this. Now, QH minimum is 7.5 megawatt, this is from PTA, and QC minimum is 10 megawatt, this value is also from PTA. So, under this constraint, our aim is to develop a heat exchange network which will not violate this. The number of units required, including heaters and coolers, are 7, because if I put the number of units target here, this is 2 hot, 2 cold, 4 streams plus 1 utility, 5 minus 1 is 4, and here there are 3 streams plus 1 utility, that is 4 minus 1 is 3. So, for this 3 units are required, and for this 4 units are required, which includes heaters and coolers as well. So, total number of units are 7 for this problem. So, we predict the number of heat exchangers for this problem as 7, and this has to be matched through our design. So, we have to match QC minimum, QH minimum, number of units, and these temperatures should start with 250 and reach 40. So, this terminal temperatures and the supply temperature has to be matched, and this flow rates has to be matched. Now, the feasibility criteria for the above the pinch area, which is called hot end, are NH should be less than or equal to NC. Now, here we have NH is equal to NC. So, this criteria is met. Now, let us see the CP criteria. CP criteria tells that CPH should be less than CPC, and this criteria we will use when we put matches. Now, we will create a CP table. So, here this is for hot streams and this is for cold streams, and these are the rules, and based on these rules, especially this rule because this is valid already. So, based on these rules we will now put up matches. So, first match we put from stream 4 to stream 3. Now, if you see the stream 4, its CP value is 2.5, this is, and 3 is this 0.3, this is 3. So, there is a match between these two. Now, if I am doing match between these two, so CPC is more than CPH, and hence this match is valid. And while discussing CP rule, we have seen that if we obey these CP rules, there is no question of delta T minimum violation, because the temperature profiles will diverge and it will never converge, and based on that the CP rules have been created. So, we put a match between this and this. Now, the match should be put in such a way that one stream should be ticked off. Now, second match we have put between this 0.15 and 0.2, this is 0.15 and 0.2. This also obeys the CP criteria, and hence this match can be put up. So, there is no violation in putting up these matches. Now, in the below pinch, we have these streams, stream number 2, stream number 4, and this is cold stream number 1. CP values are 0.15, 0.25, 0.2. 3 number stream is off here, because 3 number stream is only present at the hot end and it is not present at the cold end. So, we have this CP table here and we have to obey these rules. These are the these are the reverse rules of the hot end. That means, NH is now greater than or equal to NC, and CPH should be greater than or equal to CPC. Now, if I put this rule, NH is greater than or equal to NC, I find that NH is 2 number of streams and NC is 1 number of stream. So, this criteria is satisfied. Here NH is greater than NC. Now, we can put up a match between the stream 4 and stream 1. The stream 4 has a CP value of 0.25 and stream 1 has 0.2. So, 0.25 to 0.2. So, CPH is more than CPC. So, this match is correct. So, this is how we will put up matches on the above pinch area and below pinch area. So, once we have learned how to put matches, then we will directly put matches into the problem grid diagram and create the total hen design. Now, to find out the size of the units, that means capacity of the units, how much heat it will transfer, we will use the Teachoff heuristic. While putting matches, it is required to obey the CP rules, especially for pinch heat exchangers. but the size of the unit will come out by using the Teacup heuristic. So, let us see how to fix up the size. Now, suppose I am putting up this match 4 to 3, this is in the hot end. If I put 12.5 megawatt, then this stream is ticked off. The match will be put in such a way that either this stream will be ticked off or this stream will be ticked off. Now, in this case, the hot stream is ready to give 200 minus 150 into 0.25, that means 12.5 megawatt it is ready to provide. And the cold stream, which is 3, is ready to take 27 megawatts. So, the total heat available with number 4 streams can be given to number 3 stream, it can take, so that the 4th number stream is ticked off. By doing so, I am fixing up the size of the unit and also decreasing the number of units. That means, I will move towards number of units target. Now, once I put this 140 degree centigrade will rise to 181.7 degree centigrade, and these temperatures will be maintained. That means, this end will reach to 200 degree centigrade and the input, this is the input will be 200 degree centigrade and output will be 150 degree centigrade. Cold end, this is input is 140 degree centigrade, output is 181.7 degree centigrade. Now, the second match is such that either this will be ticked off or this will be ticked off. Now, if I find out the enthalpies associated with 1, this is 180 minus 140 into 0.2. So, it comes out to be 8 watt. So, this stream, this is first stream, is ready to take 8 megawatt, whereas the number 2 stream, which is a hot stream, is ready to give 15 megawatt. So, the hot stream is in a position to satisfy the requirement of this cold stream 1. So, it passes 8 megawatt directly to this, and hence this will be now ticked off. This will be now ticked off. Now, if I consider this as a output temperature from this, then the input temperature of this will be 203.3 degree centigrade. I can do the back calculation. Now, as this stream is ticked up and as this stream is ticked up, I do not have to bother about these 2 streams. However, this stream has got some heat available and this stream is ready to take some heat. So, let us see whether I can put a third match or not. So, third match is between this and this, because this is ready to give heat and this is ready to take heat. Now, if this has got 7 megawatt of heat left with it. So, it can directly pass the remaining heat, that is 7 megawatt, after transferring this, it can directly pass to this. So, that this will be ticked off. So, this is ticked off now, and the temperature after passing this rises to 205 degree centigrade, 205 degree centigrade. That means, the input temperature to this is 250 degree centigrade, the output from this is 203.3 degree centigrade, input to this is 203 degree centigrade and output to this is 150 degree centigrade. Similarly, the input to this is 200 degree centigrade, output is 150 degree centigrade. The input is 140 degree centigrade for this part and output is 180 degree centigrade. Once I pass this, it is 205 degree centigrade. Now, this stream needs to be heated up from 205 degree centigrade to 230 degree centigrade, and this will be done by the hot utility. So, this is the scenario with us. So, we put a hot utility here of 7.5 megawatt, and this we can calculate 230 minus 205 equal to into 0.3. So, it comes out to be 7.5 megawatt. So, if I pass 7.5 megawatt here, the temperature will rise from 205 degree centigrade to 230 degree centigrade. So, now this stream will be ticked off. So, we see that all the 4 streams have been ticked off and we have used 3 heat exchangers and 1 heater. If I use the units criteria on this, then 2 streams plus 1 hot utility, it becomes 5, 5 minus 1 is 4. So, here if we count the number of units, this is 1, 2, 3, 4. So, this 4 number of units are inclusive of heater. So, we have reached to the targeted value of units. Our hot utility requirement is same as 7.5 targeted earlier. All streams are starting with their supply temperature and reaching to the pinch temperature. So, this design has been completed. Now, hot end design we have completed, we will go to the cold end design. Now, this is the cold end scenario, the grid diagram. So, we have can put a heat exchanger between these two and its value will be 7.5. How? Now, if you see here 150 to 80, this is 17.5. So, this hot utility has 17.5 megawatts. So, this can completely give to this cold utility because it is ready to take more than that. It can take 24 megawatts. So, the total heat available with this can be directly given to this and we can tick off this stream. Number 4 is ticked off now. Now, the second match is between this and this. Now, we have if you add 17.5 plus 6.5, it comes out to be 24, because this cold utility is able to take 24 megawatts and this not cold utility, this cold stream is able to take 24 megawatt and this hot stream has already given 17.5 megawatt to this. So, remaining 6.5 megawatt will come from this stream, because this stream is already ticked up. So, it passes 6.5 megawatt from this stream and this is ticked off. Stream number 1 is ticked off. Now, if we see that the capacity of this hot stream, it is 150 minus 40 into 0.15. So, this is 16.5 So, 6.5 I have already given. So, if I minus this 6.5, so it remains 10 megawatt. So, once this load is put, this temperature 150 drops down to 106.7, but this has to be further dropped to 40 degree centigrade. So, you need some sort of heat exchanger here with 10 megawatt of capacity. So, we will put a cooler here of 10 megawatt capacity, and if we do so, this will reach to 40 degree centigrade and this stream is ticked off. Now, all these 3 streams are ticked off, and from pinch temperature all these 3 streams have reached to their target temperature. This is 2 target temperatures and this has reached to the supply temperature, plus the cold utility requirements by the PTA has been reached. That means, cold utility target has been achieved. Now, let us see that number of utility targets have been achieved or not. So, this is 3 streams, 1 cold streams, 4 minus 1 is 3. So, here we see 3 heat exchangers including the cooler. So, we have matched the hot utility and cold utility requirements, and we have also matched the hot utility requirement the number of units in upper pinch as well as lower pinch area. So, my complete design is this. So, this is the complete design of the heat exchanger network for the problem given in the earlier table. And here there is only single pinch available. Now, we see a second problem which is called design of Henn with stream splitting. In the earlier problem there was no stream splitting, but in this problem we will see some stream splitting. Now, this is the stream data which will be used to exhibit the stream splitting. There are 2 hot streams, 2 cold streams, and the Cp values are this. The delta T minimum is 20 degree centigrade. The hot and cold utility requirements are 9.2 megawatt and 6.4 megawatt. This has been done through PTA. The pinch is located at 520 degree centigrade for the hot streams and 500 degree centigrade for the cold streams, the difference being 20 degree centigrade equal to delta T minimum. Now, this is stream splitting algorithm for the above pinch area, that is hot end. We have to take the stream data at the pinch, then check whether NH is less than or equal to NC. If no, then we will split a cold stream, so that the number of cold stream increases, and we will continue doing so when this is matched. Once this is matched, we will go to the Cp matching and we will check this. If yes, then we will put a match, place a match. If no, then we will split a hot stream and again we will go via this. That means, we will check this criteria whether this criteria is met or not. If it has violated, then we will again split a cold stream. This will go on when this criteria is matched, and then yes, we will go here and we will put a match. Similarly, for below pinch This is the criteria. Sorry. Now, this is the same way I can explain this, but here you notice that this is different than this. This sign has been reversed, and similarly this sign has been reversed here. So, this is the grid diagram. These are the CP values. Here we have at the cold end we have 4 streams, and the hot end we have 3 streams. Now, this is the table. First we will go for the hot end. Here NC should be greater or equal to NH. Here NC is 2 and NH is 1. So, this is satisfied, but let us take the CP table. CPC should be greater than CPH, but what we find here, none of these 2 CPs are greater than this. So, we have to go for a splitting. CP criteria is infeasible, that is I am not able to apply this CP criteria for place making or the pair making. Now, here we see this. So, NH is equal to NC. So, this criteria is fulfilled. CPH should be greater than CPC. So, this criteria is also fulfilled. So, both criteria are feasible here. So, I do not have to bother much here, but here I have to go for splitting. So, splitting is required above the pinch. So, 0.4 has to be splitted into 2 parts. One part is 0.040 and the other part is 0.005. Now, I can put the match. So, this is the splitting which we have done, that is a one extra branch here. Now, this is 0.4 and 0.5, that means this branch is 0.4 Cp and this branch has got a Cp of 0.005. Now, this matching can be done 0.0042, 0.043 and 0.0052, 0.020, because both Cp's are more than these Cp's. So, we put a match here of 8 megawatt and the size of this match will be based on Teachoff heuristic, and we put a match of 1 megawatt here, and then we put a heater of 9.2 megawatt. Now, we can calculate here, if this is from 500 to 550, 550 to 500. So, this is 50 into 0.02, which comes to be 1 megawatt. So, this stream is ticked off because it requires 1 megawatt. Now, if I see this part, this is 720 to 520, 720 minus 520 into 0.04 comes out to be 8 megawatt. That means, this stream has a capability to give 8 megawatt. So, complete capability of this stream has been passed on to this 8 megawatt. So, this is ticked off and this part is ticked off. Okay. Now, the total capacity of this is 720 minus 520 equal to this 200 into 0.045 to 0.045, which is 9 megawatt. So, by passing heat of 1 megawatt to this and 8 megawatt to this is ticked off and this is ticked off. But the requirement of this stream is more than 8 megawatt. So, requirement is 900 minus 500 into 0.043, it comes out to be 17.2 megawatt. So, you have already passed 8 megawatt. So, requirement is another 9.2 megawatt. Now, as all the heat has been given by the hot streams, no heat is left out in the hot end. So, the heat has to be brought down from the utility. So, the rest 9.2 megawatt has been passed to this from the hot utility. Similarly, we can go design for the cold end. We can put a match here of 8.6 megawatt. Then we see that this is 520 minus 320 into 0.045 comes out to be 9 megawatt. So, 8.6 megawatt it has given to here. And what is the requirement of this? 500 minus 300 into 0.043, this is 8.6 megawatt. So, this requires, this stream number 3 requires 8.6 megawatts, it can give more. So, it has passed 8.6 megawatt to here and this has been ticked off. So, the second match is, but this was left out hot stream. So, the second match is between this and this, which is between 0.04 to 0.02, and this both meets the criteria Cph greater or equal to Cpc. Now, let us check here, this is 500 minus 200 into 0.02 comes out to be 6 megawatt. So, the heat taking capacity of this, heat absorbing capacity of this stream, cold stream is 6 megawatt. So, this is ticked and this is ticked, this is also ticked. So, we need a cooler. So, 2 coolers are put here, because this can has a capacity of 520 minus 220 into 0.04, 12 megawatts. So, out of 12 megawatts it has given 6 megawatt to here and it has ticked up this, and this has given 8.6 megawatt to here, this has ticked up this. This has a capacity to give 9 megawatts. So, 0.6 megawatts will come from cooling water, it has to be cooled down by 0.4 megawatt, and in this case 0.6 megawatt will from the cooling water, because no cold stream is available, because these two are ticked up, no cold stream is available to cool it. So, this is the capacity of my cooler. Now, total capacity is 6.4 megawatt. So, this is my complete design, and this is called a maximum energy recovery design. Thank you.